So hello, thanks a lot, Laura, both for the organization together with Thomas and for conveniently introducing some of the things I can expand on. I will then start from where you left. So the different ways of thinking about causality. So control versus temporal precedence. So we go for the first one. Then, again, within this approach, either we can assume independent measurement at each node of our networks, or we can infer our network from temporally correlated data. So look at dynamical networks. And again, as a Chinese box or Russian dolls, I don't know, I'm out of metaphors. There are two different approaches, and here I will talk about model-free and model-based investigation of these temporal correlations. So what can we expect from a causality measure in neuroscience? Two family of things. The first one is a view according to which causal measures in neuroscience should reflect the so-called effective connectivity. That is, the underlying physiological influences exerted among neural populations. So this is the typical Carl Friston view and also language, which speaks of dynamical causal modeling. Then we can have a different but complementary goal, that is to reflect dynamical connectivity without requiring that the resulting networks recapitulate the underlying physiological process. And this is the philosophy beyond Granger causality and transfer entropy. Why could we choose one versus the other? So let's say, especially when it comes to the choice of the second approach, is that, first of all, the same underlying physical network can give rise to different dynamical connectivity patterns. And let's say, if a model is more advanced, contain more things, but on the other hand, we are not sure of what the model contains, then our estimate can be faulty. Anyway, it's good to have both, and I will briefly walk you through both. So the basic idea of dynamical causal model is to have that we have several neural populations, and we have some interaction, not only among them, but also within them. And we also have external inputs. In this case, there are some things that we cannot observe and some things that we can observe. So from many neuroimaging methods, we cannot directly observe the interaction between neural populations. So what can we do? We do a family of forward models that start from what we cannot observe, so neural states and their interaction. And then we arrive to our observed signal that can be mapped as a bold signal or as an EEG signal on the scalp through the forward model, and so on. Dynamical causal modeling is based on a Bayesian framework with three main actors: the parameters, the model, and the data. So the Bayesian statistics, as opposed to frequency statistics, evaluates the probability of parameters of a hypothesis given the data. On the other hand, a p-value, even though this is a common misconception, on the other hand, evaluates the probability of having that data or more extreme data given an hypothesis. So it doesn't give a probability of the hypothesis in the frequentist view. So here, in the Bayesian framework, the main question is what parameter estimates have the highest probability given the data and the model. And so we have we give names to things. So this one is the posterior, this is the likelihood, this is the prior, and this one is called the model evidence. So the prior tells us which connections are included in the model. Then we have the likelihood. which incorporates the generative model, so what we think that our neural populations are doing, and the prediction errors. Then we have the model evidence that quantifies the goodness of a model, which is used to infer the model structure. And then finally we have the posterior, which is the probability density function of the parameters given the data and the model. And this leads us to the inference on the model parameters. So for example, the first step can be the inference of model structure. So which model, or as we will see in a minute, a family of models, has the largest evidence. So for example, two neural populations interacting in this way or in the other way. Then, once we get an idea of what is the most likely models, which parameters are statistically significant, and what is their size and sign, and which parameters are modulated by a given task or by a given condition. So, the inference of model structure is necessary. It can be reduced, so our model space can be reduced, and actually should be reduced, because otherwise our model space will explode. And so if we have some knowledge about the underlying structure, we can reduce our hypothesis to a certain group of models. So in the DCM framework, we have the Bayesian model comparison, comparing actually the log evidence of different models. And this comparison is done by minimizing the free energy. What is the free energy? Is the calculable divergence between the real and approximate conditional density minus the log evidence, or is basically a Bayesian version of the expectation maximization algorithm. Or anyway, since it's complicated enough, we can say that it's a model fit of some type. Then we have the inference of model parameters. So it's often a second step in DCM studies. So either it can be used if we have a clear winning model, and then we look at the parameters, or it can be that we have no clear winning model. And so Bayesian model averaging also takes the parameters into account. And so the final parameters are a weighted average of the individual model parameters and posterior probabilities. Finally, we have inference at the group levels. So we fit different DCM for every subject. And then we have group inference of the models, either between individual models or family of models. So in DCM, what we call family of models are, for example, models in which the modulations always happens in a certain brain area, for example, the fusiform phase area, versus modulations happening somewhere else. So within the same family, then you can have different type of intrinsic and extrinsic connectivity. Then we arrive to the winning, to the choice of the winning model, and then we do a group inference on the model parameters, either with the Bayesian model averaging across models, or when there is no clear winner, we do an inference using the parameters. So specifically for ERPs, there are different types of DCM. There is a DCM for fMRI. Now there is also the DCM for resting state fMRI incorporating stochastical dynamics. This is actually an important difference between DCM models up to 3 or 4 years ago and Grange-Koselleck transfer entropy, that the latter account for stochastic processes, but now also in DCM there is some stochasticity. So this is the typical structure of model that you have for ERPs, in which you have a hierarchy of cortical connections, basically following the work of Felleman and Van Essen. So you have bottom-up connection, top-down connections, and lateral connection. And the priors on the connections go from the forward to the backward to the lateral. And then the layers within individual regions interact via intrinsic connections. This is a scheme from a paper by Claes-Stefan 2010, which summarizes what we have said what we have said so far. So we define the model space, inference, clear winning model, yes, no, BMS, yes, no, etc. Cool. Let's just sink this in for a moment. Probably you're feeling a bit like that, but now we can move to another thing. I just need a slight break. And I go where Laura left us. Going now in model-based part. The introduction has already excellently been done by Laura. So we arrive here. We must condition the measure to the effect of the other variable. So for example, looking at the influence between y and z, we need to make sure whether it is directed and not mediated by x. So what do we do? Following the Gewicke et al. Approach, we remove x from the model, and we see if the model becomes worse. So in this case, the model doesn't become worse, so we can say that there is a direct connection between these two, and in this case, the model becomes worse. On the other hand, we have a problem. We have a problem because the activity of all the time series are not independent. Some variables share common information about the future of the system. So imagine that we have not only one variable x, but a family of variables, x1, x2, x3, which are very much correlated between each other. And they all are important in conveying information from y to z. So what do we do in the classical multivariate approach? We remove x1, and we look again at the model. In this case, the model doesn't become worse, because there are still x2 and x3, which convey information from y to z. And so we say, OK, x1 is not relevant in conveying information from y to z. Then we put x1 back in the model, and we remove x2. Again, the model doesn't become worse, because we have x1 and x3, which convey information. So we also say, well, x3 also is not a mediator of information between y and z. And the same for x3. So what will we conclude? We conclude that information from y to z must be direct, because it's not mediated neither by x1, neither by x2, neither by x3. But this is not true. So we need to take into account the fact that different variables can share the same information about the future of other variables. This is not only a methodologically interesting approach and also computational, because you can reduce the number of variables. It's also fundamental, because it allows to reply to other questions. So for example, we know that region B and C both send information to A, but what about the joint influence of B and C on A? It is redundant, it is synergistic. In order to look into this, we will go a bit into the domain of information theory. It is not so remote, let's say, from Grandian causality. Indeed, the absence of Grandian causality is summarized by the generalized macro properties. So the probability of finding x in a future state, given its past and the past of another time series, is the same of the probability of finding x in a future state given only its own past. So this is the generalized macro property. When this is violated, then we have information transfer between y and x. This information transfer is quantified by the transfer entropy. So if the two probabilities are the same, the ratio is 1, logarithm is 0, and we have no information transfer. On the other hand, when these two probabilities are different, then we have a measure of the information flowing from one series to the other. This is convenient also because we are measuring something. Grandian causality is the result of a statistical test. It doesn't measure anything. So, what do we have to do when we solve, for example, an autoregressive model? We have to minimize a risk functional, choosing from a family of functions. So for example, in the case of Grandian causality, we choose among all the linear functions of x and y, the one which minimizes the error. Then you can have nonlinear extension in which you can extend this space. So this is what happens when you have independent time series. So when x and y are completely independent, the function that minimizes the error of x doesn't depend on y, because the knowledge of y does not improve the prediction of x. If we look now at the equation of transfer entropy as an entropy rate and the equation for regression, we already see some similarity between the two of them. This framework was formalized by Barrett and Seth, that derived an elegant formulation of the fact that the Granger causality and transfer entropy are equivalent when the variables are Gaussianly distributed. And then it was extended to other quasi-Gaussian distribution. In this case, they both measure information transfer. So in real life, it's difficult to have Gaussianity. But on the other hand, we have a convenient approximate approach to start working and to mix the two things. So we have a unified approach between a model-based and a model-free formulation. Is mathematically more treatable, and then allows grouping variables according to their predictive content. So we go back to the previous question, and we go for an operative and practical definition. There are axiomatic definition of redundancy and synergy. Here we go for a predictive one, for an operative one. So if we have B and C that act upon A, we can define synergy if B and C together contribute to A with more information than the sum of B on A and C on A, and we have redundancy when B and C contribute to A with less information than the sum of variables. In order to do so in the framework, we can do it in the framework of information theory, using those formulas that we've seen before, but we can also do it in the framework of Granger causality. Here we have the formula for conditional Granger causality in a multivariate system. And then what we do a dangerous thing. We anormalize this thing. We remove the logarithm. And this leads to an interesting properties. If the group of variables x, b, beta are statistically independent and their contribution in the model for a target are additive, then we have that we can define exactly the sum of their individual contribution. This property does not hold for Granger causality definition because of the logarithm. So now, Laura, that say that the normalization is very important, then you can say, well, okay, but what does it ever mean to have an anormalized measure of Granger causality? Now you are losing any link with information. To some extent it's true, but we have to remember what Granger causality does. Granger causality is designed to measure the effect, not the mechanism. And also in another paper we say that we have a detection actually, and not a measure of this information flow in a multivariate system. So in this case, we can define synergy when the Granger causality between the group of variables is greater than the sum of the contribution, and the redundancy in the opposite case. And so we have a Venn diagram of the joint information and a pairwise index of the balance of synergy and redundancy. So an index which is positive for redundancy and negative for synergy. This tells us how we can quantify the joint information shared by variables on the future of a system, and to isolate multiplets of variables based on their informational content. If you want to play with some tools, we have DCM, which is embedded in the statistical parametric mapping software. We have multivariate Granger causality implementation that in the new implementation by Lionel Barnett, it's based on a state space, and apparently it removes a bias that we had between the full and the reduced model. Then for time varying granular causality. I didn't talk about this, so I can is Laura stuff. But we have another toolbox which is called BSmart, developed by Wally Liang. Then we have a toolbox to evaluate multivariate granular causality. Multivariate transfer entropy, which when we use the covariance as estimator, it becomes granular causality. Measures in frequency domain, and then we also have the toolbox prepared together with the Luca files on information, on joint information transfer and synergy. Okay, so thanks to my present and former student in Ghent, my collaborator Sabino, Pedro, and Laura and Thomas. And this is some references, and thank you.